Have you ever really stopped to wonder what it takes to keep the lights on? I mean, really. Today, we're diving into a huge challenge that honestly affects every single one of us. How do we manage our power grids in a world that's leaning more and more on renewable energy? Let's get into it. It's a question we almost never think about, until the Wi-Fi cuts out. The answer is this constant, invisible, and incredibly delicate dance of engineering that makes sure electricity is always there when we flip a switch.
At the very heart of the grid is one simple rule. The amount of power being generated, the supply, has to perfectly match the amount being used, the demand. And I don't mean get it close. I mean it has to be perfect, instantly, every single second. Too much power and you can fry the system. Too little? Hello blackouts. It is a seriously high-stakes balancing act.
Now, for decades, grid operators got pretty darn good at this balancing game, mostly because they were using predictable sources like coal and natural gas. But now, there's a new player on the field, a really important one, that's making the whole job way, way harder. And yep, that player is renewable energy. Look, solar and wind are absolutely essential for our future, but their big drawback? They're unpredictable. The sun ducks behind a cloud, the wind dies down, and suddenly that supply side of our perfect equation gets all wobbly and chaotic. So, if the problem is growing complexity and unpredictability, what's the solution? Well, you have to get smarter. We've got to use data to peek into the future, to see these changes coming before they can knock the grid off balance. And that brings us to the star of our show today, a smart energy load forecasting and anomaly detection system. It's a pretty powerful tool that's designed to tackle this exact challenge head-on, using AI to try and predict the future of the power grid. Okay, so how does a thing like this actually work? Let's pop the hood and take a look at how this system turns a whole mess of raw, noisy data into clear, critical insights that can help keep all our lights on. It all boils down to a pretty logical four-step journey. First, it looks backward, analyzing all the old data to see how we've behaved in the past. Then it looks forward, using those patterns to predict what we're going to need next. It also acts like a security guard, constantly watching for anything weird. And finally, it wraps all that up and delivers it in a way a real person can actually understand and use. So, step one, the foundation of any smart system is, of course, data. And we're not talking about some clean, theoretical data set from a lab. Nope. This system is trained on real-deal, hourly electricity data from the Open Power System Data Project, which covers a bunch of European countries. This is as real as it gets.
And this is where it gets really interesting. When you start digging into that data, the system uncovers all these fascinating patterns. The daily rhythm of life when we all wake up and turn on the coffee maker, the difference between a busy Tuesday and a lazy Saturday, or how demand skyrockets in the summer for AC. It even sees how we react to changing electricity prices.
So what do you do with all those amazing patterns? Well, that leads us right to step two. You feed them to machine learning models. You basically teach the machine to see all these complex connections, how time and weather and price all tie into how much energy we use. And once it learns that, it can start making some pretty solid forecasts up to 24 hours into the future.
This is awesome. It's like a little peek inside the model's brain. You can see that what happened in the past is the biggest clue to the future, for sure, but it's not the only thing. The time of day, the day of the week, and especially how much solar and wind is available, those are all hugely important pieces of the puzzle. It's a really sophisticated mix. Okay, but what about the curveballs, the things you can't predict? That is where the third step comes in. See, the system isn't just trying to guess what's likely to happen, it's also on constant lookout for things that shouldn't be happening.
So what do we mean by an anomaly here? Well, think of it as anything that just breaks the pattern. It could be a sudden equipment failure out on the grid, or maybe an unexpected heat wave that makes everyone crank up their AC at once. It could even be something as simple as a glitch in the data feed.
So for example, imagine the system sees this, a sudden, totally unexplained 35% spike in energy use. Whoa. In the world of power grids, that is a massive red flag. It could mean a major power line just went down or a generator tripped offline. The anomaly detector is built to catch exactly this kind of thing, screaming for an operator's attention before a small problem becomes a massive one.
But here's the thing. All this powerful analysis is completely useless if it's just stuck in a computer lab somewhere. The final, and maybe most critical step, is actually getting these insights to the people who need them, the grid operators. And that's done through a really user-friendly web application. Yeah, this isn't just a model. It's a complete working piece of software.
It uses modern web tech, the same kind of stuff that powers the apps on your phone, to build a dashboard and a powerful backend. This just proves it's not some academic concept. It's a robust system ready for the real world.
And this might be my favorite part. Imagine you're a grid operator and you see something weird in the data. You might have a simple question, just like this one. Instead of having to dig through a mountain of spreadsheets, you can just ask it.
Because the system has a built-in AI assistant, it can sift through all that complex data and give you an answer in normal, plain English. This makes all those powerful insights accessible to everybody, not just the data scientists. Okay, we've seen all the nuts and bolts of how it works. But now let's zoom out and ask the really important question. So what? Why does any of this actually matter?
This project matters because it's completely grounded in reality. It's using real grid data to solve the real problems that operators are facing right now, especially with renewables. It's a perfect example of how machine learning and modern software engineering can come together to tackle the huge, messy data sets that define our energy systems today.
Ultimately, this is about way more than just predicting numbers on a screen. Tools like this are an absolutely critical piece of the puzzle for building the energy grid of the future. One that's not just smarter and more reliable, but one that can actually support a massive switch to clean, renewable energy.
And that kind of leaves us with a final thought to chew on. As our whole world gets more connected and more data-driven, this is just one example of how intelligent systems are being built to manage the things we all depend on. It really makes you wonder, what other parts of our world are they going to power next? Thanks so much for tuning in.